Good day, welcome to this video. In this video, I'm going to be showing how to drive a DC motor with an H-bridge circuit. And the H-bridge circuit consists of all n-channel MOSFETs. Um, and so it's in two parts actually. So well, not really in two parts, but this video particularly is explaining two parts. So first up, to drive a DC motor with an H-bridge circuit and with all n-channel MOSFETs, and to sort of detect the speed of a DC motor using an encoder. And yeah, that's those are two parts of the video. All right, so first off, I think I'm just gonna do a brief overview of the, I guess, the circuit. Obviously, this isn't a simulated environment, but the circuit is not so different from what you see here in the real world. Actually, it's just pretty much the same. And obviously so they're all n-channel MOSFETs, specifically IRF Z44. And you could replace the top two with p-channel MOSFETs. There's a way to do that, but I haven't actually done that successfully in the, actually with the physical circuit. I haven't done that successfully without heating up the top two MOSFETs. I guess my driving of them is wrong, but this particular one that I'm gonna show is something that I'm confident in. I have more confidence because I've tried it before physically, and this is just a modification of it. So basically, these two MOSFETs are tied together. These two, the gates rather, are tied together, and these two gates are tied together. These and these. So basically, two drives are needed, right? So one drive for this pair, and the other drive for this pair. And this is the drive circuitry here. So if you were to so obviously, if you required this for two different motors, obviously you'd need two different H bridges, and in total four drives. Um, so this is the drive basically. It consists of two NPN transistors and a bunch of resistors. I'm just gonna start from this point. So obviously this is made for PWM. So let's say this node right here, M1 P1. Let's say this was a 0, then this particular switch, this electronic switch, would be open. And this electronic switch is open, this particular um the base of this second transistor is going to be connected to power. In this case, 5 volts. Actually, I think I should change this to 9 volts because it could take it. Um, so this would actually become 9. This would be connected. Well, a current will flow into the base of this transistor, and when current flows into that base, this basically becomes a short circuit. This becomes closed, and if this is closed, guess what? This node goes to ground, and therefore this node becomes grounded. So essentially, if this node is 0, this node becomes a 0. And on the other side, on the flip side, if this was a 1, this this node right here, this node, red, is going to be 0. It's going to be pulled to the ground, right? It won't be pulled out. It's going to be pulled to the ground. And this base, no current is going to flow into that base because it's connected to um connected to the ground. And if no current flows into this base, it's basically open. And if it's open, this particular node here is going to get 9 volts, right? More, not 9 volts actually. It's more like 8 volts around there, or 7.5. So this node is going to be 7.5. In essence, if this node right here is a 1, this would also be a 1. Logic 1 anyway. Obviously different voltage levels, hence the need for a driver. And as for the resistors, right? So essentially what this resistor does here is essentially limiting the current going into the base of the transistor, right? So if you look in the data sheet, let me check here. Okay, I don't have a data sheet for this particular transistor, but usually I go with a value of like 1 kilo ohm, 1 kilo ohm or 2.2 kilo ohm actually, and usually that's enough. for logic level of 5 volts there. To be safe, I think you could go with 2.2 kilo ohm and reduce that if it's if it's not working out. You should just reduce that. But it's all related. I believe if you look at any electric circuits textbook, they basically explain that about the base current, how to calculate the base current. I don't really like getting into those calculations. It kind of take too much time. So anyway, I just go with a voltage level of 5 volts here. I just go with 2.2k, and that's usually enough. For this application, I went for 1k, but it doesn't really matter, to be honest. Um, you can also go for 1k. And for this, it's basically the same thing, right? So this level here is 5 volts if you're driving from an Arduino. But so this one is 9 volts. So well, the resistors have to be bigger, you know, to prevent too much the base current, you know, to limit the base current going to the base of this transistor. So that's why this is 10 and this is 1, which is more than enough. You could actually take this value to 5k, but it's better to just work with 10k, 1k, 100 ohms. You know, it's easier, like in terms of like buying resistors. But if this was 5k, then you'd have too many, you require too many types of resistors. So it's more convenient to work with resistor values like 1k, 10k on like a, you know, on something a bit more optimized, you know, easier to get components and that sort of thing. Alright, so this is the base, this is the resistor for the base to limit the current going to base of the transistor. And this particular resistors here, those ones are the most important, right? So for this transistor to turn on, right? So if you go to the data sheet of this particular transistor, you would notice that there's a threshold. And from what I remember, I think the threshold for this is about like 4.5 or 5 thereabouts, where it actually starts to turn on a bit, where it could take a fair bit of current through it, like 2 amps or 3 amps, which is enough. And now here, there's more than that going in, so it's a good thing, right? So think of this as sort of voltage division, right? So when this is actually when this how do you say it, NPN transistor is open, when this particular NPN transistor is open, this is gonna be the equivalent voltage you're gonna find here. It's basically gonna be a resistor like this. Let's do that. It's gonna be 1k there, 100 ohms, and 10k. So this will be 100, and this is 1. And basically, what you'd get at this node and just trying to, all right, power, so that'll be +9, and then this will be the equivalent voltage at this node. And if you do voltage division here, you'd notice that the voltage at this node will be about will be literally 10k divided by 10k plus 1k plus 100, which means most of this voltage, most of this 9 volts is actually going to end up here, which is what you want. So in essence, you don't want to make this value too big. You want to leave it at 1k, just enough there. And this is basically a gauge resistor. So in this particular example, I guess for the Arduino, it's the PWM defaults switching frequencies at about 500 hertz, 0.5 kilohertz, and usually that's an okay frequency to drive a DC motor. And this essentially is a gate resistor, right? This is a gate resistor to sort of limit the current going into the gate, similar to this, I guess, but similar to this actually, yeah. But this value can actually go high, be this high. You can actually make this 1 kilo ohm if you want, because the frequency is quite low. So if you were to increase the switching frequency here, you're gonna have to take this down a bit. You have to take this down more. But for 500 hertz, this is high enough. Might actually be considered low for 500 hertz. So yeah, so that's about it. This is gonna be the equivalent circuit. That's the most important thing to know from this. You want as much of that 9 volts as possible to be on this gate um, when it's a 1, right? So I'll just explain the whole thing again. So this is basically the driver for the MOSFET, right? So what you have here is H bridge. You have an H bridge, and you need this H bridge to drive the motor, obviously for bidirectional control. So this would be for one direction, this and this would be on for one direction that way, and this would be on for the other direction, right? So you need to drive them because these MOSFETs require a certain voltage at the gate. This voltage your microcontroller cannot produce, right? So um, this MOSFET requires to drive it properly. It's actually more than 9 volts, but to have decent current flowing through it where your DC motor is not going to be slow is about 6 volts. At 6 volts at this node, it's good enough, right? So that's why, and the microcontroller can only produce 5 volts, right? You can only produce 5 volts from your microcontroller, and besides, your microcontroller cannot source enough current really for 2 MOSFETs, right? It can't do it from the PWM it produces. So hence you need a MOSFET drive. So this right here is a MOSFET drive, right? This is a MOSFET drive, and the 4 MOSFETs together makes a DC motor drive, right? All right, so that in essence is what this is. And again, and in reality, you could do this with literally you could do this with one n-channel MOSFET really. But to sort of have consistency where 60% duty cycle here is 60% duty cycle there, you know, you sort of have to add two NPN transistors. So this one turns this one on, and then this one turns that one on in that order. So I'll just explain that again. So a 0 here would cause this to be open, and if this is open, this particular base here is connected to 9 volts, right? Through these resistors, right? It's connected to 9 volts, so this will be off. So this will be on, right? So this switch will be closed. And if this is closed, this node will be connected to ground. So in essence, if this is connected to ground, this here is connected to 9 volts, this will be connected to ground, and this node will be connected to ground. So this node is connected to ground, this node is connected to ground. On the flip side, a 1 here is going to cause this to be closed, and if this is closed, this node is going to be a 0, causing this NPN transistor to be open, and if it's open, this node is connected to 9 volts. Well, kind of, according to this, right? And then you have a 1 there. So you have a 1 there, and you have a 1 there. So you have consistency in that way. But if you just wanted to use one NPN, then you just connect this right here. So you just have this, literally this circuitry right here, this circuitry, you'd have it over here. But I don't really want to get into that. You could sort of play with that on your own time, on your own when you're looking through it. All right, so that's basically it. And obviously this drive is multiplied by 4 for 4 different pairs of MOSFETs. All right, so that's that. So now I guess the second part would be for all right, for speed detection, right? So if you wanted to detect this particular speed, right, you'd have to use an external interrupt in the code, in the Arduino code, right? All right, I'm just checking to see everything is all right here. All right, so let me just go to the code. So in terms of so this is the code for the system. Actually, before I do this, let me just go through the other one quickly. So if you were to want to detect the speed of a DC motor, you could use several ways, but there's a device called a photo interrupter module. It looks like this actually. So it's a photo interrupter module, and basically there's a photo transistor on one side. No, there's an IR diode on one side, and there's a photo transistor on the other side, right? And basically what happens is it's a yeah, that's essentially what it looks like. The different views. So essentially what happens is, so this is the side. Just zoom it. Okay, it's not good. All right, so basically this is the equivalent circuit diagram that you get, right? So you'd light up the LED, and it would shine on the phototransistor on the other side, obviously through the gap, through this particular gap there, and it will shine on the phototransistor, and then you'd get a high pulse on this side through this circuit, uh, through this particular circuit, right? So I just did a bit of an example here. So in to actually sense the speed, you would have like let's say for example you had an encoder wheel with like holes in it, right? So through the holes, the LED would actually, the phototransistor part would actually pick up the light from the LEDs, right? From the particular LED that you're shining. I think sometimes it's an IR LED, but it'll pick that up, and there will be a high um, pulse on this signal here, probably closer to 5 volts, depending on what kind of voltage you have connected to the collector part of the system, part of the phototransistor. And then, because there are holes, there's a specific number of holes, right? So when there are no holes, because it's spinning, right? The DC motor is spinning, right? So when there's an obstruction, yes, I think that's the word. When there's an obstruction, right? When there's a particular obstruction, then this node will go low, because the light has been interrupted, hence a photo interrupter module, right? So again, if you have a DC motor with if you're using an encoder to try to sense the speed of the DC motor, right? There will be the encoder might have holes in it. So through the holes, when the light goes through the holes as the motor is spinning, right? This node would go up. This the how do you say it? The phototransistor will get I guess excited. I'm not sure if that's the right word, but would get a voltage on this particular node here according to this circuit. And if there's an obstruction, it will go low. This node will go low. Right. Maybe I should draw to explain. It's better. Alright. This is gonna be disaster. I hope you guys understood that explanation. Because yeah, I'm not gonna even try that. It's gonna be disaster. Alright. Yeah, so basically what the circuit does is it's a comparator, right? It's a comparator. This is a comparator, right? So and the output of this comparator will be a 1 if the voltage on the positive terminal, or on the non-inverting terminal, is higher than the voltage on the inverting terminal. Then you'd have a 1 there. But if the voltage on the inverting terminal is higher than the voltage on the non-inverting terminal, then you get a low on the output. Now we can actually take advantage of this, and with the encoder. So this is the photo interrupter module. Obviously, well, in the sim it's actually not, it's PC817, but it's a fair example circuit wise to explain what is going on with it. So imagine this is a photo interrupter module. The LED goes on. The LED is actually always on, but imagine there's an obstruction, right? So when there's an obstruction, like I said, there's going to be a 0 there, right? Or rather, this is going to be an open circuit. I think that's a better way to sort of try to explain it. So when there's an obstruction in between them, right? When there's an obstruction, like a black body or something, an obstruction, this is going to be an open circuit because this is a phototransistor. This is going to be an open circuit, and this node is pulled to the ground, so this node will be 0, right? But when there's no obstruction, i.e. a hole, a certain hole in an encoder, this is going to become a short circuit, right? When this becomes a short circuit, this node goes up to 5, right? This is going to be a 5 volts at this particular node, and this will be sort of the equivalent circuit at that point. So the resistance between this node right here, the resistance between this node and this node will be so low such as this, that if you did a voltage division, most of the voltage will be at this node I highlighted red. Most of the voltage will be there, right? So it won't be exactly 5 volts, but it will be pretty close to 5 volts, right? So that's how you get 5 volts. So in essence, as the encoder spins, you're basically gonna get like a square wave here, right? A square wave of variable frequency depending on how fast the encoder is spinning. Encoder, I'm assuming, would probably be attached to your DC motor, so the encoder frequency at which you're gonna see a square wave here will be equivalent to whatever that is, to how quick the encoder is spinning, i.e. your DC motor. Right, so now what the comparator circuit is for actually is, if that voltage does not go up to 5 volts, because some phototransistors are quite strange in how they operate. Sometimes the voltage won't go up to 5 volts. So that's why we have to tweak the voltage on the non-inverting side, right? So let's say the voltage actually does not go up to 5 volts. When the light is detected, let's say it goes up to 3.5 volts. What do you do then? And it's not 5 volts. So what we do is you put how do you say this? Potentiometer or variable resistor on the negative side, on the non-inverting terminal, to actually adjust the voltage, the threshold voltage. I think this one I can actually think I'm gonna try not to fail at this one. So what you get on the non-inverting side, so what we do basically is we tweak with this voltage, right? Okay, so the non-inverting side, right? V minus, and then basically the V plus is the one that changes based on how fast the encoder is spinning, right? As well as the light is getting interrupted and the light is getting shine on, as the light is getting interrupted, it's going up and down, right? So basically the voltage on this node is basically doing something like this, right? It's just jumping up and down like that. And it goes down and it jumps up again, right? But then what we get on the output here, which goes to the microcontroller, is, right? So like I said, the when V plus, so this one is V plus. So when V plus is higher than V minus, there's going to be 1 on the output, right? So once it goes higher, you're going to get something like this. So it's going to be a 1 there. And then once it goes lower than that V minus, i.e. when there's an interruption, it's just going to go low like that, right? And then it's going to stay low like that, until here again, when the light goes through one of the holes, right? And it's going to go high again, right? Like that, and so forth, and so on. Basically, it's gonna keep going on like that, and basically what you get here is a nice clean square wave, right? That you can actually use to detect the speed accurately, pretty accurately, right? Because that's how your microcontroller would read it, as an interrupt, right? So you get it as an interrupt here. So in essence, this is a crude speed sense circuit. Obviously, you could the more advanced speed sensing circuits out there, you know, like putting capacitors there and sort of filter out the noise. But this is a basic bare bones in essence, just to explain the working principle. You could try this out, obviously, with a really good op amp, i.e. MCP6024. This would probably work with just resistors, because this is a really good op amp. and a decent photo interrupter module. And in this case, if you look, there's a resistor here. This is 10K. So the purpose of this 10K resistor is simply to limit the collector current, right? So these different, so if you buy a photo interrupter module, right, it's probably gonna come something attached to it with telling you the max collector current that can go through it, or the nominal collector current. So in essence, you would choose a resistance value here that limits it to that. Almost like the same thing you do for current limiting LED, right? So if it's like says it's 20 milliamps, so what you'd say is you just say 5 divided by 20 times 10 to the power of minus 3. Let's say the max collector current is 20 milliamps. Not sure if this is right. Just see. So 5 divided by 10. Right, so this particular configuration dictates that the current going through the collector is is 0.5 milliamps, which is a lot less than 20 milliamps, which is what they have sometimes. And sometimes they have them as low as the max. They have them as low as 2 milliamps. So you try to stay below that value. So yeah, that's basically what you have. So I was just looking, like, so I imagine if the let's say the max here was 20 milliamps, I guess the lowest resistance you could put here would be 250 250 250 ohms. But that 250 ohm resistor would have to be a sort of, you know, um I guess it might get warm a bit because of 20 milliamps going through it. So it's just safer to go with a larger resistance value. All right. And obviously on the LED side, you have to use a current limiting resistor for the LED, based on your voltage. Obviously, that's here I usually just use like 220 ohms, so 330 ohms. Obviously, you should calculate to, obviously, it will be on the data sheet as well, the maximum current that could go through the LED. Usually 50 milliamps. So if you have 5 volts there, the minimum you could go here is 100 ohms. Probably you should go higher than that. Um, the resistance there, current limiting resistor, basically. This is a current limiting resistor as well, by the way. So that's that. Let me just give a brief summary. So this is representing a photo interrupter module. LED here is short. Well, the switch is closed, and if the switch is closed, it's going to be 5 volts here. It's going to go high. But if the switch is open, but if this particular switch is open, you have a 0 here, or it goes to 0 at least, right? So, because that signal kind of looks like this sometimes, it's not a perfect square. Sometimes it is if the photo interrupter is pretty fast. I guess you could connect directly to the microcontroller if it's fast enough. But sometimes it's not, so you have to use a comparator. So you connect that to the positive side, and the other side you connect to the negative side. You connect to a variable resistor so that you can tweak with the level of this voltage, this V minus voltage. Sometimes it could be 3.5 or 3.2, but you have to just sort of tweak it such that when this is closed, right? Such that when this is closed, you have a high here. And when this is open, you have a low there. Sort of like a square wave, right? So we have a nice square wave to put into the Arduino directly. All right, so that's that. So that's in essence the hardware part. The hardware of the describing the hardware of the system. Right. And yeah. So now I'm just gonna go to the Arduino code, which is quite straightforward, and quite a few examples on the internet. So you could just dig into that and see how to go about that. So basically, we're looking for 4 PWM channels are needed for this. If you're doing this for 2, DC motors. For one DC motor, for each DC motor, you just need two PWM channels, right? For one for each direction you want the DC motor, for each polarity, basically. All right, so here you have so these are the directions. So motor 1, polarity 1, motor 1, polarity 2, motor 2, polarity 1, motor 2, polarity 2. That's what these variables represent: 3, 5, 6, and 11. And in this particular example, right, an interrupt had to be used, the timer interrupt. But the issue is the timer interrupt actually disables some of the PWM channels. So 9 and 10 do not work because timer 1 is already being used for timer interrupt to calculate the speed of the DC motor. So those are disabled, so that's why one has to use 3, 5, 6, and 11. Yeah. So these are the variables. So this is for the how do you say, motor 1, polarity 1, right? Or clockwise, anti-clockwise. I don't really want to say clockwise or anti-clockwise because I'm not quite sure actually what direction it's gonna go. It all depends on how you connect your motor, because current can flow either way in a DC motor. So motor 2, polarity motor 1. So this is 1. So it's motor 2, polarity 2, motor 2, polarity 2, right? Alright, and the count is basically the number of interrupts that are counted, right? So if you look at this particular thing here, every time it interrupts, it counts that. So that's the variable for the number of ticks, right? Variable for that. Variable for number of ticks, right? So this is to calculate the RPM, the distance, like, I don't know, maybe you wanted to calculate the amount of distance that your motor has traveled. Let's say it was on, I don't know, some sort of car, some sort of device, and this would be to calculate the speed, obviously. And yeah, so that's how you initialize that. And all right, let me close that. So this is to obviously set up the pins M1, M1, etc. This 8 and 13 is actually unnecessary. Just do that. Probably gonna. And obviously you can find this code in the description link. Yeah, so this is the setup for an external interrupt and initialization for serial com to basically see the speed, distance, and yeah, RPM. All right, so this is the initialization from the timer interrupt. Actually, this is where there's several examples of this out there. There's actually others for like the other timers as well. So yeah. So basically what this is doing is initializing the register and initializing the counter, because every timer has a counter to count from 0 to the maximum value in it, and this is the compare value to determine the frequency. So this is the formula to calculate the frequency. The frequency of the timer in this case, what I mean, the timer interrupt, how often it's going to interrupt, right? So this particular one is for 1 hertz, which is, it's going to interrupt every 1 second. But in this particular code, I'm trying to do that every 100 milliseconds, so it's just divide this by 10. But this is the official formula, so 16 megahertz, 1 times what you call it, so there's a prescaler being used of 1024 and -1. So this is the formula to use for this, and to get it to be how do I say, for 0.1 second, 100 millisecond, this is the value to use. All right, and the rest of it is just setting up the bits for the 1024 prescaler. and it's all explained by the comment. Um, I got this code off of the code for this particular part to use there because Arduino does not it's not very intuitive to sort of do it in Arduino to just set up a timer interrupt on the fly, or unless you're just gonna have delays in your main function. So just check that out there. There are probably better ways of doing that. All right. So this is the function for the timer interrupt itself. So this is timer one comp a vect. So this is the interrupt for the timer. So this is where the speed is calculated, the speed in RPM in millimeters per second, almost like speed of a road car, and the actual distance being traveled by it. So that's what that is. Obviously I'm gonna get back to that. I just want to do an overview of everything. And here, this is the main loop, and obviously the functions have been created for forward, backwards, turn left, turn right, and stop. So these are the functions. It's basically obviously forward, M1 P1 PWM, M1 M2 P1 PWM, and the others get 0. Obviously it's just a thing where you have to figure out the polarity, etc. And halt, obviously zeros for all of them. And this is the interrupt, right? So every time the interrupt occurs, this this variable is incremented, right? This variable is incremented. That's it. That's literally it to try to calculate the speed. This variable is incremented, and then once we get into the interrupt to actually calculate the RPM, that's what this formula is for. RPM calculation formula. That's what it's for. So this is how the formula goes, right? So the number of pulses, obviously pulses is equals to count. That's what it is. Pulses, counts, the same. And in this case, the interrupt is 100 milliseconds. So it's in essence, so let's say for example, every 100 milliseconds we count 10 pulses, right? The interrupt is, interrupted 10 times. So it will be 10 pulses, but in units, to actually realize the units of that, it's actually 10 pulses per 100 milliseconds. So now the challenge is to convert 10 pulses per 100 milliseconds to revolutions per minute, right? And the way to do it, the best way that I know how to do that is just manipulating the units, right? So pulses per 100 milliseconds, you multiply that by 1000 milliseconds in 1 second, right? But I want to change that to minutes, so we say multiply by 60 seconds divided by 1 minute, right? So now we've converted this milliseconds to minutes, right? And the next thing to convert is the pulses, right? The pulses to revolutions. So um how many pulses represent one revolution? That's the main thing to know. So right, so if let's say your encoder, whatever you're using, your encoder wheel had, let's say, I don't know, 30 interruptions in it, like 30 holes in it, this would be 30 pulses. You would experience 30 pulses every revolution. So that's the value you choose here. In this particular example, in the Proteus simulation, this was actually 240, right? So 240 pulses. And that's how you'd calculate the RPM. So whatever you get here, the counts, you would multiply it by everything else. So in this case, it's 2.5. So if you calculate doing this, so it's going to be 1000 divided by 100 times 60 times 1 over 240, right? That's 2.5. So obviously I don't want to, I can't really punch it into Arduino like this. This is more to explain. So it's going to be count multiplied by 2.5, and that's how you get your revolutions per minute. And like if you wanted to get it in speed like a road car, then you'd have to do more calculation. Same. What you have is pulses per 100 milliseconds. That's what you have. Like let's say it's 10 pulses per 100 milliseconds. You do the exact same thing, but this time now you want seconds, right? You don't want minutes. So you just say multiply by 1000 milliseconds divided by 1 second, right? So they're 1000 milliseconds in 1 second, right? And then the next part is actually to take the pulses to millimeters. And for that, what you want to do is you first off, you want to convert the pulses into the revolutions, same as up here. So what you have there is just do that, right? Aligned. So you have one revolution is 240 pulses, right? In this particular example, it all depends on what type of encoder you use and how many holes your encoder has, right? So that would be, I don't know, 30, 35, 40, I don't know what that is. But in this particular example, it's 240 pulses per revolution. So you'd have 240 pulses here representing one revolution. Now you're trying to take revolutions to normal units, right? To linear. So this is circular, I don't, revolution wise, circular, yeah, circular motion, yeah. So this is circular, you're trying to take that to linear. So one revolution represents 2 pi r in linear, right? So this is basically the perimeter, the formula for the perimeter of a circle. That's what this is. It's 2 multiplied by pi multiplied by r, the radius. So whatever wheel you're using, your encoder wheel you're using, not encoder wheel, actual wheel, you'd have to calculate, measure rather, you have to measure the radius of that wheel, or the diameter. Just measure diameter divided by 2, and that's what this would be. And that's how you'd convert from the revolutions to the linear part, which is, right, this, to the linear part in like a straight line, right? Yeah, so let's just go over that again for speed specifically, because I think revolutions per minute is kind of intuitive because it's all circular, right? But for speed, so you'd go first off from pulses per milliseconds. You take that to pulses per second, which is essentially what this part is right here. Oh crap! From this part, this, right, that part there. That's taking it from pulses per milliseconds to pulses per second, right? So once you go that route, now you have it in seconds, right? Because remember, the target unit here is millimeters per second, right? The denominator is seconds. Great. Now the numerator is what you're trying to achieve now. So first off, you want to convert the counts that you got, or pulses. You want to convert that to revolutions. How many revolutions does that represent, right? So in this case, 240 pulses represent one revolution, right? And what does one revolution represent? Linearly, right? Linear. So what does one revolution represent? Linear, right? So when your motor goes one revolution, when the wheel goes one revolution, how far has it moved in a straight line? Essentially what that is. And with that way, the easiest way, obviously accounting, ignoring friction and all those other things, pretending like the surface is smooth and perfect, right? You'd have to say circumference. You have to relate that to the circumference of the circle. So one revolution is this in a straight line, as long as you take friction out of the way, right? So that's 2 pi r, and that entails you measuring actual radius of your wheel, right? And then you get that. And this is essentially the formula you use to calculate the speed. And distance is just accumulated, and distance, the formula for distance is speed multiplied by the time, right? And what is that? Just accumulated, basically. We're just accumulating that. So you have to add the previous distance to the current distance, cause you keep moving, the wheel keeps moving, so you can't minus, you know. I guess you can, but why would you want to do that? Your distance is adding up. Yeah, so this particular one, so for this, it's actually going to be 1000 divided by 100 multiplied by 1 divided by 240 multiplied by 2 times pi times r, 2 times pi. So in this case, I'm assuming like the wheel that I'm using in this case is what, 60 millimeters. That's what I'm assuming, right? So the radius is gonna be 30, right? So 30 divided by 1, right? And the value here is gonna be 7.854. Great. And here, obviously, speed multiplied by time. Obviously, here in the original code it was occurring every 1 second, but now it's 100 milliseconds, so this is 0.1. This is the time, 0.1. Remember, this time coincides with your interrupt. Time your interrupt time happens every 100 milliseconds or 0.1 second. And that's how you get that. Alright, and obviously you have to take count back to 0 because you don't want that messing up your readings, so you want it to start all over. And obviously this is just to read out to the terminal so we know what's going on. Alright, so again, RPM, pulses per 100 milliseconds. And if you were to change this time to 10 milliseconds, you'd have to make that change as well. Remember, this is on its own. When you're actually trying to get the value for 2.5, essentially what you're punching into your calculator is going to be one from this side onwards, right? Onwards. So this pulses is already intrinsic in your code. It already knows that. That's the counts. That's the number of counts. So you have to multiply that by 100 divided by 1000 divided by 100 in the case of 100 milliseconds, multiply by 60, multiply by 1 over 240. Obviously this ribs and whatever, I just put that there to, you know, boost understanding of what it is that's going on in this particular equation. And obviously if your interrupt was 1200 milliseconds, whatever the time is, you have to make that adjustment right here in milliseconds, because that's going to be pulses per whatever milliseconds. And for speed, it's the same thing. The only difference here is no minutes anymore, unless you wanted to calculate your speed in millimeters per minute. Why you'd want to do that, I don't know. But if you wanted to calculate your speed in millimeters per minute, or whatever units you want to do, then you'd make that adjustment. But in this case, you know, let's say you want to do it in millimeters per second, right? Then you would do it as such, or millimeters per hour. If it's millimeters per hour, then you have to extend this to multiplied by 60 minutes divided by 1 hour, etc. to actually get it, the speed an hour in millimeters per hour. Right. But in this case it's millimeters per second, and everything stays the same like I said, except you have one revolution. You have 2 pi r millimeters divided by 1 revolution. So this part, this is it's a nightmare highlighting. So this part here, this and this, right? So that's the only difference to actually get the circular into linear. So yeah, that's about it. That's about how to calculate that. Yeah, yeah. The most important thing is knowing how much pulses you're getting, and obviously the most difficult part is actually positioning of your particular sensor on whatever it is you sense in the wheel, etc., and having the proper circuitry behind that. And that's the most important thing. And now we're just gonna demonstrate that. And well, Proteus is set up. Well, this is an external library, so it's not very stable. So it can actually run only one DC motor at the same time. So I'm just gonna close that and run this. Run this code. Well, run this first. Alright. Alright, so just do that. Copy that. And once you press play. Oh, my bad, I forgot to add the display for the virtual terminal. And just do that. Add that. Right. So now speed unit visible. And so here 100 milliseconds. So that's the speed right now that it sensed. Obviously updates. So now it's 10. As you can see, it's a bit lagging behind because of CPU processing, etc. Yeah. motor is getting closer. Well, it's not actually going to get close to this until this reading here, like sort of flat lines, becomes more stable. So this top part, this is the speed in RPM, speed in millimeters per second, and this is the total distance traveled in millimeters, 28.21. Distance traveled in. As you can see, they're getting closer to one another. The problem is this keeps changing, right? And this has to basically catch up to it. Yeah. So that's that. So that's forward motion. Now I'm just gonna change that to reverse to the other way, the other direction. So be reverse 150. So 150 is the PWM out of a maximum 255. Guess the Arduino is intuitive to use that way. And once you play that, you can see it's spinning in the other direction. As you can see there, it says minus there, but the speed display reading is pretty much the same, right? It's the same encoder there. But in this case, of course, the encoder is embedded here in the simulation, but in the real world, you kind of have to make that yourself. Yeah, so that's that. Just do that. And now I'll show the other motor in action. Guess I have to add that again. You can see reverse. So I guess there's something's gone wrong. Alright, it's operational. You can see it's spinning the other way. And obviously I haven't connected the interrupt here. And also that's one thing I want to mention. For this particular configuration, if you wanted to detect speed of both motors independently, you're gonna have to migrate your system to a bigger probably you could use a PIC or use a bigger Arduino. You have to use a bigger Arduino because if you look here, the PWM is already taken up for int1. So int0 is the only one available, so you can only detect the speed of one motor, realistically. I think I should attach that just to show. It's int, alright, and yeah, so readings will be getting received. There's a bit of a delay, and because this is being simulated, so there's a delay. As you can see, same speed being detected. It has to sort of catch up with this, and this is reverse, obviously. Let's change that to forward. Obviously, there are other ways to realize the H bridge, but this particular way to do it has several advantages. One of which is you could do it with just n-channel MOSFETs, and yeah. Well, the disadvantage of this is a lot of MOSFETs, basically. Price, I guess. A lot of MOSFETs, and yeah. So now it's forward again, and literally left and right is just gonna be variations of the forward and reverse. There's kind of no point into sort of doing that. and for some reason it cannot simulate both of them at the same time. Yeah, so this is the drive, and the drive's pretty much, it's the exact same drive, just one like this 4 times. And this particular NPN transistors do get expensive. If they're unavailable, two N3904s are equally as good, not as powerful, but work just fine. They work just fine. 2N3904s. Shucks. 2N3904s works just as well. Yeah. Let me just change back to 2232. Alright. Alright, I'm trying to make sure I'm not forgetting anything. Oh. And yeah, so yeah, that's one thing to keep in mind. So we have the speed there. And also, before I forget, it's important to note that you could also use um a logic level MOSFET for these MOSFETs, but it's important to know that using an n-channel MOSFET for the full bridge has certain disadvantages, especially using this particular driver structure, right? So the obvious disadvantage is obviously when you're driving both of them together, right? The how do I say this, right? So there's always going to be a resistance here, right? There's an on resistance here, which means this node is actually not directly connected to ground, right? It's not necessarily directly connected to ground. It's connected to ground first by this, by the resistance, the internal resistance of the DC motor, and the on resistance of this MOSFET. Hence why these particular MOSFETs are being used. So the resistance of this MOSFET is very low. The on resistance is very low. So it's almost like it's being connected to ground, but it's just in a high side configuration. Whilst if you use the P channel MOSFET, it wouldn't be that way. It would just be because it's the polarities like are sort of opposite to the N channel MOSFET. So it's almost like its ground is actually 9 volts for a P channel MOSFET. So when the source has to be connected to 9 volts and the drain actually connected here. So that's one advantage of using P channel MOSFET over N channel. But in this configuration, if you were going to use a logic level, I advise not to do that, not to use the logic level, because logic level MOSFETs have high on resistance. The on resistance are quite high, and basically the motor won't be as fast as it would be in this configuration, right? I mean, and I doubt the microcontroller will have enough to actually run 2 of them, like actually tie these 2 together. I think it just shut down if there's no actual driver attached. So overall, this might cost a bit more in terms of the MOSFETs, but it's better chance of working. Actually, it will work better than a logic level MOSFET. And you can try using P channel up here, but obviously it's slightly different drive circuitry to this. Um, yeah, but this is about it. This is basically how you would go about designing a driver for an H bridge that drives a DC motor. And also I wanted to add, you could, for I guess flyback protection, you could add motors, diodes such as these. I find that these help, especially when you're trying to monitor the current going through. Let's say when these 2 are on, some sort of current still flows through here, you know, to sort of limit that, and to, yeah, basically you don't want current flowing in a direction you don't want it to flow, hence you would use these diodes. Yeah, I'm trying to make sure I'm not forgetting anything. And yeah, so if I sort of missed anything, you have questions regarding this code or schematic, please do ask. If I am available, I will try to respond. Yeah, and obviously the code will be available, and yeah, and the description and the schematic is this is it. Like, this is just the way it looks, and right. All the best with your applications. You know, I guess building a system. Cheers. Bye.